RNAV1 or RNP1. RNAV1 or RNP1 refers to precision navigation within the terminal area of the airport for departures or arrivals, with a navigational accuracy of plus or minus 1 nautical mile 95% of the time, or an RNP1. Coverage is provided by use of station-referenced navigation signals, or within the limits of a self-contained system capability, or a combination of these. Required navigational performance, RNP. The capability of an aircraft to contain navigational accuracy within a specified radius up to 95% of the time. For example, the requirement for basic RNP5 is an ability to maintain containment within plus or minus 5 nautical miles of centerline 95% of the time. RNAV GPS Standard Instrument Departure, SID. A published departure procedure from an airport to the en route airway structure that uses RNAV RNP capability to navigate. RNAV GPS Standard Arrival, STAR. A published arrival procedure that transitions from an en route airway structure to the final approach fix for an instrument approach in the terminal landing area using RNAV RNP navigation capability. Track to a fix. A course which connects two terminators or waypoints within the database, controlled by the FMS to compensate for known wind drift. Displayed on the navigational display, ND, as a solid line connecting the waypoints. History of performance-based navigation. The desire to free aviation from dependence on fixed routes defined by ground-based navaids, a concept known as free flight, has produced technologies that permit more direct flight from point to point and a greater number of routings through a given airspace. More efficient use of airspace increases capacity, saves fuel, and achieves benefits such as noise reduction by avoiding densely populated areas. Realizing this, the aviation community started to implement area navigation, RNAV, back in the 1970s. RNAV implies a method of navigation enabling an aircraft to fly on a desired flight path using any chosen means, traditional navaids, self-contained systems, or a combination of these. The related concept of required navigation performance, RNP, implies RNAV plus other capabilities. Although internationally agreed upon, public standards for RNP and its relationship to RNAV are still evolving. Work continues in this area, and a number of carriers are reaping the benefits. Several years ago, Europe introduced basic area navigation, BRNAV, with track following to a normal accuracy of plus or minus 5 nautical miles of the course center line. BRNAV enabled significant capacity gains, some direct routes, better feeder routes into terminal areas, TMAs, and reduced dependence on terrestrial navaids. RNAV is an acronym for Area Navigation, so called because aircraft routes are spread over a given area, rather than being fixed with respect to ground-based navaids that have to be overflown. These more direct and efficient routes can be flown using satellite-based and other self-contained systems, traditional navaids, or a combination of both. Onboard RNAV systems can be standalone or included as part of the Flight Management System, FMS. There are two broad bands of RNAV capability. Basic RNAV, BRNAV, referred to as RNAV Type 5, is used for en route navigation and can be supported by relatively unsophisticated navigational equipment. Precision RNAV, PRNAV, known as RNAV Type 1, is a much more precise navigation standard, suitable for use in terminal areas. Traffic separations must allow for the navigational accuracies of the aircraft involved. Compared to the current situation, the most important aspect that PBN offers is the consistency in RNAV RNP procedure design, and execution on a worldwide basis. This in itself provides a safety benefit and is main driver for the introduction of PBN procedures in worldwide terminal airspace. Considering PBN as an appropriate requirement for terminal airspace RNAV operations, it becomes the enabler for RNAV RNP operations in terminal airspace, providing all the associated RNAV RNP benefits. Fewer radar vectors also means less uncertainty on the flight deck with regard to the anticipated tactical route and the distance to go. As seen on the arrival to Schiphol Airport, runway 6, in Amsterdam, one can see the amount of traffic flying over towns and other airports using ground-based nav aids and radar vectors. Using PBN, one can see that most inhabited areas are missed on the arrival. PBN allows aircraft to increase noise abatement procedures, improving the environment. Since both PBN SIDS and STARS use step climbs descents, less fuel is used during these procedures. Less fuel burned means less pollution released in the atmosphere. Step climbs descents allow operators to arrive at the termination of the procedures at a safe altitude to transition to the next section of the flight path. Operators using PBN allow the reduction of congestion on the ground. As such, the worldwide consistency brought about by common PBN application will enhance the safety of RNAV RNP operations in terminal airspace by addressing, in particular, common airworthiness and operational approval, common ATC procedures. Given the worldwide consistency offered by common PBN application, the absence of national RNAV RNP applications means that RNAV RNP terminal area procedures will be available for use for all operators and not only national operators. Above and beyond the worldwide safety advantages that PBN provides, the enhanced accuracy capability of PBN-approved aircraft means that less airspace is required to accommodate PBN terminal area procedures. As such, capacity and environmental benefits can be obtained. For example, specific SIDS, STARS, can be designed to accommodate different environmental requirements for night and day operations. Viewed from a worldwide strategic perspective, the application of PBN in worldwide terminal airspace is to be viewed as a pragmatic step towards RNP-RNAV application, which will form the basis of PBN terminal area procedures in future. PBN is part of the airspace concept to standardize both en route and terminal procedures, like BRNAV and PRNAV, that can be used on a global basis. The new standards will require more stringent navigational accuracy, augmented aircraft sensors, implementation procedures, and mitigation of aircraft separation procedures for increased safety, while reducing the need for ground-based navigational aids and controllers. At present, the industry is in a transition to PBN at the time of developing this program. Procedures like BRNAV and PRNAV have been combined into PBN. In the United States, a different navigational standard is presently used, but will eventually adopt the PBN standards. In this program, we will compare and contrast the present with the expected PBN procedures and standards. Comparison of present and future navigational specifications, OCEANIC remote navigation. Presently, over most of the oceans or remote locations, the standard demonstrated navigational performance is RNAV 10, or plus or minus 10 nautical miles either side of the center line. This is also referred to as RNP 10. PBN will refer to this as RNAV 10. In the North Atlantic, the current minimal navigational performance specification, MNPS, of RNP 12.6, or plus or minus 12.6 nautical miles either side of the center line. Now, using RNAV 10 on some North Atlantic high-level airspace HLA routes. These standards require at least 2 onboard long-range nav aids, GPS, IRS, or both to maintain this standard. Over specific oceanic routes, the navigational accuracy can be limited to RNP4, or plus or minus 4 nautical miles of center line. In addition to the 2 onboard long-range nav aids, an operator would also have to have controller-pilot data link communication, or CPDLC. This allows continual position, altitude, and other data link communications with controllers while in the airspace. As you can see, there are 3 different standards for different parts of the ocean. PBN will standardize this initially to a standard called RNAV 10 for the majority of the ocean, and RNP4 for those operators that have the CPDLC capability. In addition, the operator must have a capability for ADS-C to operate in RNP, RNAV4. At this point, mostly airlines are equipped with CPDLC capability, but some corporate aircraft are now being modified to include CPDLC. However, new NAT high-level airspace routes use RNAV 10. En route navigation. There are many different standards for en route navigational specifications. Presently in Europe, BRNAV or RNAV 5 plus or minus 5 nautical miles of centerline is the standard. In the Middle East, RNP3 is the standard. In the US, the airways extend 20 nautical miles either side of centerline on jet upper routes and 4 nautical miles either side of centerline on Victor low routes. As you can see, this can be very confusing depending on where you fly internationally. The US also has published Q and T routes, which require RNP2 capability and approval. A Q route is an upper direct RNAV routing between points without the dependency of ground-based nav aids. A T route is a lower route, which also depends on onboard navigational capability. PBN is going to establish continental standards of RNAV 5, 2, and 1 as a global en route navigational specification. As you can see, very few changes other than terminology, but these standards would apply globally. The dependency on ground-based nav aids will be reduced during this period of transportation. Terminal area navigation. Presently, SIDS and STARS are flown to different specifications depending on the procedure, the capability of the aircraft, training of the pilots, and approval of the state of registry. In Europe, for example, arrivals and departures are flown to RNP5 or RNP1 specifications as published. This is the same in the US. Under PBN, the navigational standards will remain nearly the same. RNAV 5, 2, 1, or Basic RNP1. The Basic RNP1 can only be used on SIDS and STARS so published. Note, outside of 30 nautical miles from the field accuracy is limited to plus or minus 2 nautical miles. What is the difference in RNAV1 and Basic RNP1? The navigation's specifications of RNP4, Basic RNP1, and RNP Approach all have specific monitoring and alerting requirements for the pilots that are not required of RNAV 5, 2, and 1 procedures. These 3 navigational specifications require 4 characteristics. An accuracy of plus or minus 1 nautical mile, 95% of the total flight time, as monitored by onboard systems. Performance monitoring by aircraft systems and or the pilots to a required limitation. Duplicate aircraft systems to back up any system failure during critical phases of flight, and a limitation on the loss of GPS signal. Any of these failures and requirements will be reported to the pilots so they can transition to an arrival, departure, or approach with less stringent requirements. RNP Approach has a navigational limitation of RNP1 on the initial, intermediate, and the missed approach segments of the approach. The final approach segment of the approach is limited to RNP 0.3. Continental en route navigation, RNAV 521. General purpose of PBN in en route navigation. We will discuss the general purpose for PBN usage in worldwide continental airspace. and include some of the advantages of this navigation procedure over previous methods. Then, we will discuss the airworthiness requirements for equipment and precision navigation requirements for use of this form of navigation. Finally, we will discuss the normal and contingency procedures needed to safely fly using this navigation system. En route navigation can be to a navigational standard of RNAV 5, 2, or 1. In the following discussion, we will address RNAV 5, but the same procedures and limitations will apply to all three standards. But we will limit the discussion to RNAV 5 to reduce redundancy. RNAV 2 is limited to a plus or minus 2 nautical mile limit.